your attention, please? We are about to start. Everyone, please be seated. Yeah, could you please be seated? Swadika. Good morning, ladies and gentlemen. First of all, I would like to welcome and thank you, all of you, for taking your time to be here today. My name is Arisara Chaikitiratana. It is a great privilege to be your MC and moderator for today's seminar. On behalf of the organizing team, it is an honor to extend a very warm welcome to the esteemed guests, special invitees, honorable speakers, and all the participants to this technical seminar titled Natural Fiber Plastic Composites for Automotive Applications. This seminar is co-organized by King Mongkut's University of Technology North Bangkok and the National Science, Technology and Innovation Policy Office, together with the great collaboration support from Merge Cluster of Excellence, Germany. This seminar aims to offer insightful knowledge and expertise from top-level experts on the technology and the application of natural fiber plastic composites for automotive and other products. As we know that Thailand is rich in natural fibers resources, also plastic, and we are also plastic and automotive parts exporters. This seminar will give a very good opportunity to the participants from the industry as well as academics and also researchers to learn from the invited speakers and somehow to apply the knowledge into practice or into new innovations. This will be certainly beneficial and can strengthen our country's industrial competence. We are very much honored and privileged to have with us today a large ensemble of experts and specialists from Merge Cluster of Excellence, Germany's first and only federal cluster of excellence in the field of lightweight composite structures, and from Crossfire, the world-renowned injection molding machinery and automation system manufacturer. Also, we are also have a great privilege to have special guest of honor, the president of King Mongkut's University of Technology and director of Opole University, Poland, to give a welcome and opening speech today. To begin with this morning's session, I would like to take this opportunity to call upon Professor Thiravuth Bunyasopon, the president of King Mongkut's University of Technology, to deliver his welcome speech. Please join me in welcome Professor Thiravuth.
First of all, may I apologize for being late due to my prior commitment with the Secretary General of the Higher Education Commission. We have with us this morning the honorable guests from Germany and Poland. First person, Professor Dr. Marek Tukendorf, Rector of Opole University of Technology, Poland, and his another position, Excellent Council of the Federal Cluster of Excellence Merge. May I welcome you to our university. Will you please stand up? Will you please stand up? Yeah. Okay. He's okay. He's very tall and handsome guy. Another friend of mine is Professor Dr. Ing Habil Lota Crow, Director of the Institute of Lightweight Structures and also he's also the dean of the Faculty of Mechanical Engineering at the TU Chemnitz. And we have this is another 7 keynote speakers from Germany, German University, Chemnitz University of Technology, and Dresden University of Technology, Germany. May I ask you to give a big hand to all of them. And ladies and gentlemen, Dr. Alisara Chayiti Ratana is our outstanding senior lecturer and future president of this university. He already told all of you about what we are being here to exchange the skill and knowledge, including the experience from our guest lecturer and professor from Poland and Germany. I just want you to know that we have this conference or seminars. We have a very great collaboration from the overall University of Technology Poland and the Chemnitz University and also the Dresden University. So we have a very great honors to have the academic collaboration with the 3 universities from Poland and Germany. And of course, all of us here in this room would like to welcome our guest speakers and the guest of honor from Germany and Poland to our university again for the second conference. I just want you to know that since we have more Thai participants than foreign participants, may I give you permission to speak in Thai so that our people can understand better than my English conversation. การจัดการสัมมนาในครั้งนี้นั้นเราได้รับความร่วมมือเป็นอย่างดียิ่งนะครับจากสำนักงานคณะกรรมการนโยบายวิทยาศาสตร์เทคโนโลยีนวัตกรรมแห่งชาติซึ่งสวทน.นั้นได้กรุณาให้การสนับสนุนทั้งเรื่องทั้งอินคายกับอินแคชก็คือทั้งผู้เชี่ยวชาญจากโปแลนด์แล้วก็เยอรมันแล้วก็จากประเทศไทยเพราะฉะนั้นเนี่ยสิ่งที่ทำให้เราได้เห็นภาพของการจัดอินดัสเทรียลเซมินาร์ในครั้งนี้นั้นเนี่ยก็เป็นเพราะว่ากระทรวงวิทยาศาสตร์และเทคโนโลยีในส่วนของสวทน.ได้รับผิดชอบดูแลในเรื่องนี้ตามนโยบายของรัฐบาลซึ่งมุ่งเน้นให้มหาวิทยาลัยทั้งของไทยและก็ของต่างประเทศนั้นได้รวมตัวกันเพื่อที่จะผลักดันให้เกิดนวัตกรรมใหม่ขึ้นมาให้เป็นประโยชน์ต่อการออกแบบผลิตพัฒนาแล้วก็ขายให้กับประเทศต่างๆทั่วโลกเพราะฉะนั้นเศรษฐกิจของประเทศไทยจะเจริญก้าวหน้าได้นั้นต้องอาศัยทุกท่านทั้งหลายที่มาในวันนี้เป็นผู้ที่ช่วยเป็นเครือข่ายในการที่จะถ่ายทอดนวัตกรรมใหม่หรือ innovation ที่จะเกิดขึ้นตั้งแต่นี้ไป ในอนาคตนั้นถ้าเราไม่ร่วมมือกันเราก็จะสู้ประเทศต่างๆในอาเซียนแล้วก็ประชาคมโลกไม่ได้เพราะฉะนั้นความมั่นคงของประเทศชาติของเรานั้นจะอยู่ได้เนี่ยต้องอาศัยความร่วมมือร่วมใจกันของภาครัฐโดยรัฐบาลสถานศึกษาโดยมหาวิทยาลัยหรือสถาบันวิชาการขั้นสูงที่เกี่ยวข้องแล้วก็เทคโนโลยีทรานสเฟอร์จากประเทศผู้นำด้านอุตสาหกรรมซึ่งก็หนีไม่พ้นเยอรมันกับโปแลนด์ซึ่งเป็นประเทศผู้นำด้านอุตสาหกรรมในปัจจุบันเพราะนั้นเนี่ยผมมาในวันนี้ก็มาเพื่อที่จะต้อนรับทุกท่านเข้าสู่มหาวิทยาลัยเทคโนโลยีพระจอมเกล้าพระนครหลวงของเราแล้วก็มีสิ่งใดที่ขาดตกบกพร่องในการต้อนรับในวันนี้เนี่ยก็ต้องขออภัยด้วยเป็นอะไรก็ตามเราหวังว่าเมื่อท่านมาในวันนี้แล้วเนี่ยเราสามารถที่จะสร้างเครือข่ายความร่วมมือทางวิชาการโดยเฉพาะยิ่งเน้นในเรื่องของการวิจัยและพัฒนาแล้วก็การถ่ายทอดเทคโนโลยีซึ่งกันและกันนะครับเพื่อที่ให้เกิดศูนย์รวมข้อมูลหรือเกณฑ์ knowledge management ในบริษัทของท่านที่จะแลกเปลี่ยนเรียนรู้กับมหาวิทยาลัยเทคโนโลยีพระจอมเกล้าพระนครหลวงและมหาวิทยาลัยต่างๆทั้งภาครัฐและเอกชนของบ้านเราและก็ต่างประเทศสิ่งหนึ่งที่จะฝากไว้ก็คือถ้าต่างคนต่างทำต่างคนต่างคิดต่างคนต่างลงทุนโดยที่ไม่หาพาร์ทเนอร์หรือผู้ร่วมคิดร่วมทำให้เป็นเครือข่ายในการที่จะสร้างนวัตกรรมใหม่ขึ้นมาเราก็จะไปไม่รอดประเทศชาติเรานั้นทุกวันนี้จะอยู่ได้ก็ด้วยความสามัคคีกันของภาครัฐและเอกชนเท่านั้นเราต้องพึ่งตัวเองให้มากๆถ้าเราพึ่งต่างชาติมากเกินไปเราก็จะไม่โตไม่เจริญเติบโตทางเศรษฐกิจเป็นตัวเองอะไรก็ตามที่เราผลิตไปก่อนเราจะได้เปรียบในเรื่องของราคาในเรื่องของการส่งออกในเรื่องของการที่จะยึดครองตลาดโลกได้นั้นสิ่งเหล่านี้เนี่ยเป็นสิ่งที่พวกเราทุกคนต้องร่วมมือกันมหาวิทยาลัยแห่งนี้เป็นมหาวิทยาลัยของรัฐบาลตั้งโดยรัฐบาลเยอรมันตั้งแต่ปีพ.ศ. 2502ซึ่งในช่วงนั้นเราเรียกเทคนิคไทยเยอรมันเรามาเป็นมหาวิทยาลัยเทคโนโลยีขึ้นมาเนี่ยก็เพื่อสร้างคนแล้วก็สร้างเทคโนโลยีให้กับประเทศชาติของเราโดยที่จะต้องร่วมมือกับภาคเอกชนให้มากขึ้นนั้นทุกวันนี้เราอยู่ได้ก็เพราะความสามัคคีกันของภาครัฐและเอกชนก็ปัดตรงนี้ไว้นะครับแล้วก็ดูการที่อีกครั้งหนึ่งขอบคุณอย่างมากคือโปรเฟสเซอร์ดร.มาเรตทูกินดอฟPresident ของ University of Technology Poland แล้วก็ท่านอีกตำแหน่งหนึ่งซึ่งสำคัญมากคือท่านเป็น Excellent Council of the Federal Cluster of Excellent Research ซึ่งเป็นองค์กรด้านวิทยาศาสตร์เทคโนโลยีที่สำคัญของประเทศยุโรปในเครือยุโรปนะครับแล้วก็ทั่วโลกแล้วก็ต้องขอบคุณอีกครั้งหนึ่งคือโปรเฟสเซอร์ดร.อินอาบิวโรธาโครซึ่งเป็น Dean of the Faculty of Technical Engineering ของมหาวิทยาลัยเคมบริดจ์อีกตำแหน่งที่สำคัญมากในเรื่องของResearch and Development ก็คือ Director of the Institute of Lightweight Structuring ซึ่งมหาวิทยาลัยเคมบริดจ์นั้นเป็นมหาวิทยาลัยชั้นนำของประเทศเยอรมันและยุโรปไม่แพ้มหาวิทยาลัยอาเซียนเหมือนกันนะครับก็ขอบคุณอีกครั้งแล้วก็คนที่ผมจะต้องขอบคุณจากส่วนลึกของหัวใจผมเนี่ยมากๆเลยคือรองศาสตราจารย์ดร.อิสราไทยกิติพัฒนาที่อยู่ฝ่ามือผมนะครับตบมือให้ท่านนะครับ แล้วก็รองศาสตราจารย์ดร.สุชาติเอกสินนะฮะที่ท่านอยู่ตรงนี้นะครับท่านทีมงานของทั้งสองท่านนี้ที่ร่วมมือร่วมใจกันให้มีวันนี้ขึ้นมาได้นะครับแล้วก็ขอบคุณสวทน.เป็นอย่างมากที่สนับสนุนให้ภาครัฐเอกชนได้ร่วมมือกันพัฒนานวัตกรรมใหม่ซึ่งเราก็รู้อยู่แล้วว่าในเรื่องไฟเบอร์พลาสติกคอมโพสิตสำหรับออโตโมทีฟและแอปพลิเคชันมันสำคัญมากในบ้านเราแล้วถ้าเราฝันก็เหมือนว่าเราจะเป็นผู้ที่ผลิตและพัฒนารถยนต์ทุกรูปแบบเป็นอันดับหนึ่งของอาเซียนนั้นเนี่ยก็น่าจะเป็นความฝันที่เป็นความจริงถ้าทุกคนร่วมมือร่วมใจกันนะครับขอบคุณอีกครั้งแล้วก็ขอต้อนรับทุกท่านสู่การสัมมนาในวันนี้นะครับแล้วก็ท่านอธิการบดีของมหาลัยจากโปแลนด์ก็คงจะมากล่าวเปิดการสัมมนาผมมาในฐานะเจ้าบ้านมาต้อนรับท่านด้วยความเต็มใจแล้วก็มาขอข้าวของวันท่านทานหนึ่งมื้อนะครับวันนี้ก็ขอบคุณดร.วิศรัยท่านนะครับขอบคุณสำหรับกาแฟที่วางไว้ให้ด้วยขอบคุณครับ
For a very insightful and remarkable welcoming speech. Next, I would like to take opportunity to call upon Professor Marek Tukiendorf, the Director of Opol University, Poland, and also a member of Excellent Council of Merge, Cluster of Excellence, to deliver the opening speech for today's seminar. Please welcome Professor Tukiendorf.
Distinguished Professor President Teraputi, dear Vice President Sushar Sikam, distinguished Professor Walter Crow, Professor Hartung, Savadika, Schönen guten Morgen, very good morning. In my language, Dzień dobry. First of all, let me thanks for the invitation to this great event. It's really an honor to my delegation and to my university, Opole University of Technology. It's one of 15 Polish universities of technology in my country. We are really very proud just be present over here today and just to have this possibility to collaborate in this excellent team. We are a member of the Cluster Merge, led by Professor Walter Crow. We've been in very good connection for many years with the Technische Universität Chemnitz, with the Professor Walter Crow and Chancellor Dr. Eberhard Alles, the Honorary Doctor of King Mogund University of Technology, North Bangkok. I would like to express my deep gratitude for, as I mentioned, possibility to participate in these 3 days workshops. I am more than sure that we will gain a lot of benefits, fruitful benefits to every part of this meeting. I would like to propose to President Teraputi just to begin the future collaboration between my university and the King Mogund University of Technology in North Bangkok. And I hope that we will be ready till Wednesday to sign the letter of intent in frame of our future collaboration. So let me thanks for your attention, and I wish to you and to myself a lot of fruits, a lot of benefits of this scientific meeting. Thank you very much.
Thank you. Thank you very much, Professor Tukiendorf, for a remarkable opening speech. And now our seminar is officially opened. And I would like to take this opportunity to call upon Professor Tiravut to present a token of appreciation to Professor Tukendorf. Please. Professor Tukendorf, please step forward, please. Professor Tiravut would like to give a token of appreciation for every speaker to this seminar. Please, Professor Crow, please come forward. Next to Professor. Okay. Okay, so next Professor Vakenfa. Professor Vakenfa. Professor Vakenfa, please. And next, Dr. Trosh. Dr. Trosh, please come forward. Next is Dr. Roth. Next is Ms. Siegel, Caroline Siegel. Okay, next, Mr. Amin Oli. Okay, Oli, yes. So now our seminar is officially opened, and I would like to proceed with. Oh, okay, sorry. Before we begin our seminar, we would like to take opportunity to take group photo for. Okay. Professor Crow would like to give a small gift to Professor Tiravut.
So, ladies and gentlemen, we doesn't not work yet and have get a lot of presentation. So we have also some gifts for Professor Tirabuti, and one is our symbol of a merge cluster. It's a triple helix. It's for collagen, which is also in our body to bring all the things together. And this is a symbol to bring together perhaps our university, King Mogul University, Chemnitz, and Opole University in the future, and we are the same strategy to make some good things for the future. Yes, and this is for you.
Try for it. So I am safe.
Please, all the speakers, please step up to the stage, and we would like to take a group photo. Next, it's my great pleasure to introduce you to our first prominent speaker, Professor Roland Crow. Professor Roland Crow is CEO of Cluster of Excellence, Merge Technologies for Multifunctional Lightweight Structure. He is also the Dean of Faculty of Mechanical Engineering at TU Chemnitz. Also, he's a chair of Lightweight Structures and Polymer Technology TU Chemnitz as well. And recently, he has been given an honorary award and the Medal of Honor of the TU Chemnitz. There are about 200 scientists and researchers working under him, handling more than hundreds of academic and industrial-related research projects. We are so thankful that he can allocate time in his busy schedule to be with us today. He will fly right back to Germany after this lunchtime, and this is how busy he is. He's a very busy man. Okay, ladies and gentlemen, please join me in welcome Professor Crow.
Alexander, thank you for the nice and kind introduction. I think it's better. Yeah, it's better. It's good. No, I think it's good. It's wrong. It's wrong. It is good. Thanks very much for the invitation, ladies and gentlemen. Good morning for the conference of the topic natural reinforced composites, and especially a lot of greetings for my friends from Technical University of Opole, Professor Tukendorf, Professor Wagenvier, Professor Hartung, and all the scientists which organize this conference, for the support here in Thailand. I like to be here to speak about cooperation and perhaps future projects, because I think we speak about one of an important topic. Why it's so important? I will present it. Why lightweight structure is so important? Why natural fiber reinforced composite also important. And yeah, it's like a start lecture. I will speak about the resource efficiency in the production of fiber reinforced plastics, about a topic which is the strategy of a cluster of excellence merge. It's one of the biggest project in Germany, and so it's not possible to speak about all the details, but what we mean about resource efficiency. Because you know there are a lot of ways and parts to make resource efficiency. We deal only with one part due to the lightweight structure. This is the agenda. Speak about motivation, lightweight approach, bivalent resource efficiency, about the research domains and the transfer of this to application of the companies, to work together with the companies. And yesterday we have a nice evening dinner on the boat, and we already spoke with small and medium enterprises of Thailand, and I think it's also a beginning of a cooperation. For some of you which don't know where is Chemnitz, Chemnitz is in the heart of Europe, 3 kilometers south of Berlin. Berlin is more famous than Chemnitz, from the large city. We are established since the 3rd century. It's the 3rd largest city in Saxony. The population is not so big like in Bangkok. We have 240,000 people in Chemnitz. And some perhaps unique constellation, excellence research and bright perspective. We have a collaborative research centers, non-academic research partners, Fraunhofer institutes, close connection to the industry, PhD academy, and intensive network, what we use also for the cluster of excellence. Here you see the cooperation partners in the world, and you see also the King Mogul University in Thailand, in this part. I have a laser pointer here. And our counselor is responsible for the consortium 21, and this is also a network of different universities. 2008, Her Royal Highness Princess Cirindron visit us in my labs. I start in this time in Germany with the first machines, and we were very proud, and that Her Royal Highness visit us, and I here explain some injection molding parts, and we also have a compounding natural fibers. These are wood fibers, and this was also the first step, I think, beginning with our counselor, Eberhard Alles, who get the degree, doctor honorary degree, doctor of philosophy of King Mogul's University. I think it's begin in this time. And after that, Professor Tiro Butti signed a cooperation agreement with our counselor, was our rector, previous rector. So and now we develop such cooperation, and I am very proud and happy that we not only have a university cooperation, but also that Krauss Maffei as one strongest partner of our industry partner, but they are also here, and Mr. Holzinger, CEO, he come also to this session, and we spoke about the future cooperation. Now perhaps some detailed information, what is MERT, why in Chemnitz, and we have a small movie. I think we start if you can better, faster understand what we are doing in this cluster. I hope it's work. We are engineers and it have to work.
Germany's Industrial Revolution was sparked in Chemnitz and its region. From here, continental Europe's growing needs for textiles and milling factories were answered, making the German Manchester. And it was Chemnitz and its region where the manufacturing of cars first started. Through all the fundamental changes and historical upheavals the Saxon region experienced in the 20th century, the place and its people were able to nourish and revive the essence of their success. With its spirit of entrepreneurship, its highly skilled workforce, its unique concentration of small and medium-sized companies, and its position in the heart of Europe, the region leads the innovation of key enabling technologies. The driver of its success was the early and close collaboration between the University of Technology at Chemnitz and the numerous small and medium-sized companies. Right after reunification, industry and academia, together with the newly founded Fraunhofer Institutes and other research units, pooled their strengths to develop projects and establish startups. With the creation of the Smart System Campus in 2006, they have created the perfect environment for the joint design and production of key enabling technologies. The Smart Systems Campus, with its generous dimensions on a site measuring almost 4.5 hectares, brings together a number of scientific and technical research centers, including the Fraunhofer Institute for Electronic Nanosystems, the faculties of Electrical Engineering and Information Technology, as well as Mechanical Engineering, the Institute of Lightweight Structures and Polymer Composites, the Institute of Physics, the Center of Integrative Lightweight Technologies, and the Fraunhofer Institute for Machine Tools and Forming Technology, all of which are in close proximity. These cooperative infrastructures, with their interdisciplinary orientation, have spurred the development of hybrid technologies based on fundamental textile, plastic, and metal processes, as well as the integration of micro and nanosystems. Pioneering the energy-efficient production of lightweight structures and composites. The partners in industry and academia are central players that steer the future development of lightweight constructions and carbon technologies as key enabling innovations. A unique environment is the Alliance for Textile Lightweight Construction. Here, the Institute of Lightweight Structures, the Institute of Conveyor and Plastics, with the affiliated Institute for Textile and Processing Machines and the Saxon Textile Research Institute, work together with more than 350 regional, small, and medium-sized companies. Thus, the Alliance is coordinating more than 350 research and development projects in the fields of textile technologies, lightweight structures, and lightweight system design. Thereby, they have created more than 600 jobs, primarily in Saxony, in the high technology sector. Consequently, the last central program for innovation in medium-sized business placed the cooperation first in Central Germany. Acknowledging the leading role of this strand of research and design, the Saxon Excellence Initiative awarded a major grant to explore energy-efficient ways of production. Moreover, in the latest highly competitive German Universities Excellence Initiative, a consortium led by the Institute of Lightweight Structures and Polymer Composites was again successful in securing a major grant. In order to bring scientists together and to merge technology processes, a new building, the Merge Technology Center, is being built. Here, boundaries between separate fundamental technologies will be made permeable and eventually eliminated so to enable resource-efficient technology fusions for multifunctional lightweight structures. With its general focus on the energy-efficient production saving materials and power, as well as the sensible use of technologies, the collaborative environment thus addresses the major task our society has to address.
So, thanks very much. It was a short introduction to the cluster of excellence. Why we are doing, why is lightweight structure so important for the future? You see it perhaps on this slide. The weight reduction, all branches, automotive and airplane, they would like to reduce their weight. And you see that the government give a requirement in USA, in Europe, and in China, and in the whole world, because when you reduce the weight, you reduce the carbon dioxide emission. And how it does work, you see here the weight reduction of 100 kilo, and the Volkswagen Golf 7 is a standard car in Germany. They already now reduce the weight up to 100 kilo. You can reduce the carbon dioxide emission near 8.5 gram per kilometer. So, for example, I have a Passat, a diesel Passat, a standard car also, and I drive. Arizara said I am a very busy man, so I have to drive a lot of kilometers, and I drive in the year 50,000 kilometers in Germany. You know, in Germany a lot of big auto cars and highways, and it's possible to drive very fast. And for this 50,000 kilometers, when you calculate it, you can reduce with this 100 kilo, you can reduce for one car, for my car special, a half a ton, 500 kilo per year. It's a lot. And we have in Germany 50-60 million cars, so it's a very big number. When you reduce the weight, you can reduce the carbon dioxide and you save the climate. This is our goal, I think a very, very important goal. So we have also, but increasing the prices and shortage of energy, you know this problem with greenhouse effect, and you have save the energy and decrease the carbon dioxide emission. So we are in the strategy we come to the goal, resource efficiency along the whole entire value chain. we are in the topic of lightweight structures. And we have to bring all the actors together, OEMs, automotive, small and medium enterprises, scientists of academic staff, scientists of the non-academic staff. And it's a big challenge to reduce the carbon dioxide emission. This is the goal of a cluster of excellence. And now in the numbers, because it's interesting to see it in the numbers, when you produce a car with an auto engine, of a standard car, you have 20% of this coming from the production, from the greenhouse gases. It's an analyst study of Audi. Audi is also a car from Volkswagen company, and it change when you have change between the production and operating number. When you have a car with electric engine, you need you have 50-50 due to production and operating. This is for auto engine and operating. And our goal is to reduce it till 2020 in this period up to 50%. This is our big goal. It is possible to reduce we've mentioned lightweight structure, but also to reduce it in the production process. And examples, once again, car, I mentioned it, 100 kilo weight reduction, 1 liter fuel per 100 kilometer. This was approximately 1 kilo per 100 kilometer. And in the airplane, it's more important per weight reduction. You have 4 kilo per 100 kilometer less carbon dioxide when you reduce 100 kilo weight. When you have 100 kilo weight reduction. So it's important. And now we work also of a weight reduction in the topic that we make the components more intelligent. Why it's so important? Because you know the smart walls in all the branches. You have smart cars, smart cities, smart mobility. The cars communicated with each other, the building communicate, smartphones, all its network, big network, and how to put these sensors and actors in these processes. Lightweight approach, a very big topic. I am not able to explain all the details, so we concentrate on the fiber reinforced plastics, because it's a bridge to the natural fiber reinforced plastics. And I will more explain why it's now important to work with new technologies for composites. And we have one special example now in Germany, because in Germany, is also in Saxony, the BMW i3 are produced. And this is the first car in the world where we have a serious production of a carbon chassis. The first car in the world, they produce it, 30,000 units in the year. The car is very expensive, it's a small car and costs 30,000 euro, a lot of money, but the production costs are so expensive. The technology is so expensive because it's a new technology. And you see here when we compare the kilo prices of components for steel, the components, structure prices. It costs 5 euro 1 kilo. Aluminium costs twice, 10 euro per kilo. And carbon reinforced, now which is in the car, cost 100 euro. Compared to steel, we have 20 times more. This is not the production for the future. So we look for new technologies for resource efficiency, and when we reduce, when we increase the resource efficiency, we reduce the prices. The prices have to come perhaps to 20 euro per kilo when we are happy, and the automotive branch is also happy. You see, this is our research field. So what is in the different branches? Space flight, aviation, they pay in the space flight 40,000 euro when they reduce 1 kilo. It's a lot of money, but it's very important to reduce it. Aviation pay 4,000 euro when they reduce it 1 kilo. And automotive only 10. So it's important now when we would like to bring the composites to the standard car, it is necessary to reduce the price of the production. So we need a jump from this cost to a high lightweight degree. This is the principle. What we need. So this is the topic of cluster of merge. To see the triple helix, what I mentioned, metal, plastics, textile, microsystems. We bring this together and look for very fast processes where we can bring together the different materials. And we look for now for technologies which are already now suitable for series production. Which technologies are suitable for series production? When you see such parts here, a lot of parts are made by injection molding processes. Injection molding process is very fast technology. You put all in the mold and you make a one shot, and the complex component is ready. So it's a reason why we work close together with Kausmaffei, because they develop new machines. We need special machines or modified machines and modified processes to do it. This is the reason for this. And in this cluster, Federal Cluster of Excellence, we have 14 institutes, 3 institutes of TU Dresden, 14 of Chemnitz, 2 affiliated institutes, 2 Fraunhofer Institute and 1 Leibniz Institute. Together there are 100 employers which work in this consortium for 5 years. Yes, and me and Dr. Tölsch and Dr. Roth, we are COO, and we have managed it. It's not so easy to manage 38 professors together. Sometimes it's difficult to manage 2 professors. 38 is more complicated. So I mentioned it, but we use key enabling technologies which are already technical mature. So call it inline processes and in situ processes. Inline processes are processes roll to roll. They are for closes. They are also roll to roll. They are very fast processes, and the injection molding processes also very fast. We call it in situ. Other people say one shot, one part, the same name, or of a process in one heat. Kausmaffei, every branch has own a name, but it means the same group. We say to this in situ processes. And we have interactive research domains. And the structure, organization of this, Professor Village, Professor Hartung, no, Professor Village is responsible for semi-finished products. Professor Drossel is coming from Professor Neugebauer, is responsible for metal technology. I am for plastic and textile. Professor Gessner for micro and nanosystem integration. This the structure. We have also some brochure when you need some more detailed information. You get it also in the internet. And we try to bring together this technology, the inline processes. We make a semi-finished products, put it in the mold and make a one shot and cope with all materials come together and like a marriage, a good marriage of all things. And we would like to demonstrate it by our own car, Chemnitz car concept, triple C, where we present and demonstrate it when new components. You see some new technologies which are already developed because the project is running now 3 years. We have first results. Here you see a fiber foil tape. Here coming unidirectional reinforcement, rovings, and we put it together with plastic foils in one process, and so we produce our own organic sheets. And yesterday in the evening we spoke about coconut fibers, and it's also possible to use natural fibers. My experts talk about this in detail, but we can use such technique. We have this technique. Put straight coconut fiber in this with this technique between the foil, and the foil we can from the thickness, so we can design it that we have a spatial volume of the fibers. And when we can unidirectional foil make a reorientation, make a lay up, which have this spatial layout for these forces. Here you see also a new idea of a machine. We now make a manufacture a prototype. It's for a profile. It's like a wounding machine. I think you know the wounding machine. No, vice versa. Wounding machine. The fibers are coming from like a satellite where make a rotation of these rings, and you make like a pultrusion through these satellites. So a new pattern which we developed. We now are trying to build up this construction. Here also one spatial combination of a metal and plastic process. Daimler in Hamburg is a specialist of these processes. I think Daimler in Hamburg is also the only one company in the world which use this combination of the processes for lightweight structure in the automotive. You combine metal hydroforming processes with injection molding processes. I think the partners here from Kraus Maffei know this combination. It's worldwide, I think, the first, and they earn a lot of money because they have like a monopoly of this structure. The hydroforming processes is done in the plastic mold. This is very important. You save a mold tool because you do it in the plastic mold. Very, very good combination, and they already bring it up to market before we think about the combination process. Not all things is possible to combine, but this is one example where it works and where the company earn money. In the IRC, textile and plastic-based processes, I think I don't explain it in detail because for our lecture they spoke about this combination processes, about natural fibers especially. In the IRD, we integrate sensors in the structures for the structure health monitoring. You know, in plastic it is possible also to integrate the sensors and actors in the structure. You can put it in the mold, in the shot of a plastic, and you have a ready structure, and you have no connection points, because this also increase their weight. Yes, of course, we have calculated with a new tools, multi-criterial finite element methods. This is my field. I'm advanced mechanical computation engineer, and I say to all my technology-oriented scientists that I can calculate all things, but I'm not able to produce it. Because calculation, finite element, it's also very difficult. But a lot of the scientists tell me that they can also produce things what it's not able to calculate. But I think this world, the virtual world, to bring together with a real world, this is also a benefit, the synergy. Here we work with new tools of multi-criterial calculation and optimization, because we have different materials, and the different materials have different properties. And to bring this together, that they, after the process, also fulfill the requirements of the loads, it's not so easy. And the metal has another thermal expansion coefficient, like plastic. It's only one problem. You see here some new tools which we developed, especially here flow of high viscous plastics. Dr. Trilch prepared here in PhD the Navier-Stokes equation. To solve the Navier-Stokes equation is difficult, but here we have to add the Brinkmann term, and when this equation is so complex that as an engineer it's not possible to solve it. We need mathematics people, experts, and they can do it. For engineers, I think it's too complex. What we can learn from the nature, because we are dealing with fibers, and the nature don't like when they cut the fibers. The nature make a reorientation of the fibers. And this principle we would like to use in the technical application. And so we develop such thermomechanical flowing. It's not one example. You see here the stress concentration factor is very high in anisotropic materials, more than 10. So you have to, when you have a cut off, you need 10 much more of a thickness. This costs money. So when you make a reorientation, like a tree, you can reduce the concentration factor. It's one example. How we do it with drilling, we have friction, we have heat, and when it come outside, the fibers go to the side. When we have from the metal like adapter, and when we have a connection point made like in the nature, like by trees. This is the idea how to bring the principles from the nature to the technical application. This is one example. We make a patent, we make some nice project with small and medium enterprises, and now one small medium enterprises near Chemnitz, they sell such machines for the hybrid connection points with metal with carbon reinforced thermoplastic. So, and it's not possible to speak about all components and demonstrators. You see here we have a different projects, sub-projects, and we look for different components in the roof, wood lead, and we get some 2 cars from Volkswagen. It's a Volkswagen Up, and now we destroy this car, and when we rebuild it with new components, and we would like to present with this car the lightweight for the future, lightweight for serious production with new materials. And one important point are the natural fibers. About this will speak Professor Wagenfield about these components for the future in natural fibers. One example I would like to show you what we already developed with the Volkswagen concern, with Volkswagen company. It's a battery mounting. It's battery mounting for the Audi R8 e-tron. It's like a Tesla car from Audi. It's an answer of Tesla. They also developed Audi. Would like to show that it's also possible with Audi to design such car, and we are responsible for this part here. We need a technology fusion, carbon reinforced thermoplastic, and we win here a competitive. We get in 2012 the first innovation prize of the Volkswagen Group. We are very happy because it's a worldwide champions of the best lightweight structures, and we get the first prize worldwide. And my scientists and we, of course, also are very proud that we get this prize. We use here a new machine, a modified machine, injection molding machine. It's not a Krauss-Maffei machine because it was also a competitive Euro. Competitive, and they win it, but the next generation is coming from Krauss-Maffei. We have a rotating table, and we have a station. We have to produce it in serial production very quickly, and we cut it, and we have a cutting transfer in the mold in the first station. In the second, we put the inserts in the injection molding, in the mold, the shot. They are integrated. We have no screw or welding or such. Welding we have with the organic sheet, but no the classical connection points. And how it works, you see it here. You see the machine. The part is in this dimension, but not so big part. But you see here this cutted organic sheet. They are now you have now a preheating of an organic sheet when the robot put it in this rotating table with the mold with this adapter. We have now forming. The first step is forming. We have to do the drape simulation because we need that all fibers are stretched in the component because otherwise we have no strength and no stiffness. When it's rotate to the other station. We have now a preheating after the forming process. When it go to the main mold, now we have the injection process with insert integration. You see here the finite element simulation of the filling process. Now we have a second preheating organic sheet, and when we put the bottom line up and the structure is ready. And we have a common reinforced thermoplastic component, which is 30%. We have a 30% weight reduction compared to aluminium parts, and very quickly process. So you see here now the next generation of a machine. It's a machine from Kraus Maffei with a rotating plate. Here's the plate rotating. This is now installed since 2 months in the mulch cluster of Sande. A very big machine, 2,500 tons, and shot volume 11.2 kilo. It's very big parts, so we can produce parts in the one-to-one dimension. For example, for a door on a wood lead, some bigger parts. And you see the machine here is our Ministry for Finance Ministry, and our now building not ready, will be ready at 1st of October. We have an opening ceremony of this. Here you see this research hall, and when the next step. So we think at August we are ready for the next step of the technologies. And with all, thanks very much. I give you some short overview, briefly overview, and perhaps you have some idea compared to our ideas to make us cooperation in this field. Thank you very much.
Thank you very much, Professor Crow, for your very informative and impressive presentation about the state of the art of the modern technology of manufacturing, mass production of thermoplastic composites. It's very impressive. You already got the token of appreciation, so we have no more gifts for you, sorry. Okay, thank you very much, please. Thank you very much. Okay, so actually I forgot one thing. I need to ask the audience whether you have a question for Professor Crow. Do you have any question? มีคำถามไหมคะ ถ้าไม่มีคำถามจะเขียนในกระดาษมาก่อนก็ได้นะคะ มีคำถามไหมคะตอนนี้ไม่มีนะคะไม่มีถ้าไม่มีก็ขอต่อไปเลยนะคะเอาจริงๆเดี๋ยวนะต่อไปต้องพักใช่ไหมคะ Okay, sorry. So we're going to have a coffee break for 15 minutes. Yeah, for 15 minutes, and we come back again at around 10:20, something like that. 15 minutes. Okay. glass of water. You on the next one? No, after. Yeah,
Wo soll ich denn mal hinstellen, wenn Sie hier sprechen? Auf der Folie. So I know also a lawyer and I'm a research engineer for 5 years now. And I just submitted my doctoral thesis 2 weeks ago. And this process control. Yeah, because he has a flight, shower first. I think it's China or Taiwan, I'm not sure about this. I did not speak to him. So thanks.
ใ
Jest to passport. Passport needed. Okay. Maybe here. Okay. Should be right. Audio as well, yeah. Okay. I think I can give you back the VGA connector. Ich würde sagen, wo ich das nur platzieren soll. Die stört sich hier, glaube ich, sehr.
รุ่นอยู่กับเดือนเหรอคะเป็นปีหนึ่ง
Ja, bei mir dasselbe Problem, so einfach nicht zwischen
มาดูโปรเจกต์อย่างใช้เองหรือว่าลักษณะสีค่ะเป็นยางเป็นยางชื่อยางอะไรอะ
Okay, we're about to start now. Everybody, please be seated. Please be at your place. Be at your seats. Okay. So, it is my pleasure to introduce you to our next speaker, Dr. Jürgen Krosch. He's Administrative Director of Cluster of Excellence, MERGE, and he's also an Academic Council of Institute of Lightweight Structure at TU Chemnitz. This is where he earned his doctorate degree from as well. He is specialized in the area of injection molding and thermoplastic composites. He has published many papers on these topics. Ladies and gentlemen, please give a very warm welcome to Dr. Jürgen Krosch.
Thank you, Arisara, for this kind introduction. Welcome also from my side. And so I would go straight forward in our topic. And it's a pleasure for me to say now something for new technologies, for thermoplastic-based natural fiber composites. And what I would like to talk about is to go first a little bit deeper in details of principles of fiber reinforcements for polymer matrix composites. This is something we need in the next slides and to get a better understanding why we need some special techniques for getting thermoplastic-based natural fiber composites, because we always have a straight influence of the material and of the material behavior to the resulting properties in the part. And as you know, in the manufacturing process, the process has an influence of the mechanical of the polymer properties, and this also then of course in the properties in the fiber reinforced parts. And so we have a strong influence process on the relations in the morphological structure of the polymer and in the fibers, like fiber orientation, fiber length, and so on. And this has an influence of the properties in the resulting part. And then I want to give a brief overview on thermoplastic-based technologies, which is, in our opinion, more interesting than thermoset-based processes, due to what Professor Kroll already mentioned, due to the cycle time and to recycling, for example, and so on. And we will come straightforward then to some typical thermoplastic-based technologies which are interesting for natural fiber-based composites. So give an insight on technologies which are typical for all fiber-based composites, glass fiber, carbon fiber, and so on, but with a focus which also can be used for natural fiber composites. And then we have a next step with technologies which then are presented from my colleagues. So in special I want to say something only short of overview to extrusion technology, because this is, I think, state of the art and this is common used. But going more in details than injection molding, combination, compounding, injection molding, long fiber thermoplastics, and then we need something inside in the pre-breaks, because we have some technologies where we need some special thermoplastic pre-breaks, so pre-impregnated materials which we can use in techniques which are suitable to result in longer fibers in the part. And why we do this I will explain. And then have some special insights in compression molding, injection molding combinations, and some outlooking insert molding, in-mold decoration, which is not typical for fiber reinforcement, but for decoration process you can use, for example, natural fiber composites like veneer, something which then will be introduced from Professor Wagenführer, Caroline Ziegel, and Amino Ali. Okay, so when we look on fiber reinforced composites, we have three so-called paradox, or we call laws, which are responsible for thinking in fiber-based composites. And this is a law of fiber form, of the clamping length of the fibers, and of the bonding properties. Because these three big laws or paradoxes, like we know, are responsible for all the typical properties resulting from a combination of fibers in a matrix. So this is a big thinking why we make a reinforcement with fibers and not with something other, for example, like a massive reinforcement of injection molding with some metal plates or metal, something compact in big dimensions. Because some theoretical thinking, what the authors should have in mind, when we reduce the geometry of some material, we get a lowering or a decrease of statistical amount of voids inside. So I think this is a typical thinking why we use fiber. So as lower the material geometry, especially as lower the diameter of a material until we come on a fiber form, as higher the specific strength and also the specific tensile modulus. So this is something ruling to all materials in a fiber form, but especially is something interesting for our fibers, for reinforcement glass fibers, carbon fibers. And now when we are thinking on natural fibers, this is not so easy to reach because it's a natural material, and we cannot reduce the fibers to a diameter like we have in with carbon fibers on 7 micrometers, typical, or diameter of glass fibers on at the moment typical 14 micrometers. So here we have a specific influence of natural fibers that we cannot decrease the fiber diameter as much as possible. And so also in the material morphological structure, it's not a homogeneous material like glass, or more or less homogeneous material like carbon fibers. So natural fibers are totally different. This is something we go in detail. I think my specialists some mention, and we have to look on a fiber form which yield to this law as small as possible, but it's natural limit for natural fibers. Okay. So something what also rules really good for natural fibers is the fiber length, the clamping length. So maybe you know a typical tensile test, and now imagine you have a single fiber, you clamp it, and you make a tensile test. So as shorter the clamping length is, as higher is the specific tensile strength of the fibers. This is all the rules, for example, here for a flex fiber. You see, we come to an really increase of the tensile strength when we have a lowering of the clamping length. So, now, so imagine in a part you have not a clamping of the fibers, but what you have is the embedding of the fibers in the matrix. And so normally you can say if a fiber is totally impregnated, so fully surrounded with a matrix, you would have a clamping length going to zero because you have no free length of the fiber between the matrix. If the matrix complete surround the fiber, we have a really good embedding in the clamping length, so that means the free length between the clamping of the fiber would be nearly zero. So, well, why I'm saying this is something which gives an hint to impregnate the fibers as good as possible. Because if you have some voids in the impregnation of a textile with a matrix, with a resin, you should avoid to have some air, entrapped air inside, or some voids, because then you get some free clamping length, and this will decrease the specific properties, tensile strength, and especially also tensile modulus. So for all processes, you have to ensure for a good fiber matrix composite that you have a good impregnation. So for normal extrusion, you know, for example, wood plastic compounds in the extrusion process where I have short wood fibers, you mix with a thermoplastic melt. In extrusion you have not these problems, not so much. But when we think to go on composites with longer fibers, we have to take a textile prepreg, textile material with longer fibers, and then the impregnation, especially with the thermoplastic melt, is a big issue to get this, to reach high specific properties. And this is something I will speak about later. So first is to get good fibers with as much as possible, low as possible diameter of the fibers, and as low as possible free clamping length, means as good impregnation as possible for reinforcement effect, especially to get good tensile modulus and tensile strength. Okay, so this is something theoretical, but this thing of this paradoxon, you get you have a basic to get good composites. Okay, now when we look on a fiber, and this is something typical for glass fibers or carbon fibers, but also is valuable in with other qualities for natural fibers. We have a matrix. Well, matrix is weak. So if you only have a matrix, for example, thermoplastic polypropylene, you have a tensile modulus of 2000 MPa, so it's not so much. When you have a glass fiber, let's say something when you can reach around about 70,000 megapascal, and you have in the composite something between it. Okay? So especially this is valid for the tensile modulus, valid also for the tensile strength. And then we have big differences in, for example, impact properties. So what we call the property to storage energy if you have an impact from outside, what we call, for example, you test with a Charpy impact. So it's a property of the material to allow to resist against an impact, to energy storage. And now when we look on the properties, well, you have to look first on the right upper corner. We have the properties, tensile modulus and tensile strength in compared to the density. So we have here our classical carbon fibers in a huge field where they are situated. It depends on the type of carbon fiber. You have good tensile strength, you have a tensile modulus, you have good tensile strength, density, something, depends also a little bit on the fiber type, and we are something between natural fibers we have here, something between, of course, steel and natural fibers, but steel, of course, you have a high density, so it's not something you can take for classical reinforcement for lightweight construction. So you see, of course, the overall tensile modulus and tensile strength of some typical natural fibers are not so good, but the density is really low. Yeah? So this is something you always have in mind on the property in relation to the density. This is what we call a lightweight degree. Of course, not have in mind the costs to produce the part, but this is something we always have to look. Okay, let's make a part from glass fiber reinforced thermoplastics. What properties we have, what decrease or increase of the weighting compared to other materials. Yeah, and this is something you get a short overview to typical reinforcements, carbon fibers, glass fiber we have here, steel as a typical compare, and here some natural fibers. Okay, so.
The sizing of the cylinder is what is that mean for the sizing?
Sizing? You mean the surface treatment? Or?
Yeah, no, the size of the graph.
Oh, the dimensions.
But what is sehr groß?
Oh, it means why it's so, yes, it's different is you have different types of carbon fibers which cover some areas. You can make this, yeah. So, well, for example, in typical steel, the tensile modulus is always the same. Yeah. So when you use carbon fiber reinforced plastics, you have a wide field of combinations, type of fiber, type of I know what you mean. It's not the single, the poor fiber, it's the fiber composite. With this material you can make. It's not the single fiber, it's the fiber composite properties. Sorry. So depends on fiber volume, content, and something like this. So it's the area you cover, the properties you can make with carbon fiber composite. Okay, so something to the fibers now, getting the insight why we are focusing on thermoplastic processes. I think this is something typical looking on thermoset processes. The processing time over the viscosity and temperature for producing the parts. So when we look on typical thermoset process, for example, erasing, transfer molding, some liquid composite molding, typical, you have a viscosity of the thermoset resin, you mix it, and curing starts. So in the first reaction time, the viscosity goes low, goes down. This is what you use for impregnating the textile prepreg with matrix. The viscosity is really low. And then during curing, with a reaction kinetic, the viscosity increases rapidly. And then you have some curing time, let's say, of typical liquid composite moldings, not some seconds, not some minutes. Well, it depends on your metric system, but normally you're longer than half an hour, 1 hour, 2 hours for producing the part. This depends especially of the reaction kinetics of the thermoset resin. And first you have a temperature, control temperature, and the reaction starts. If you want, normally it's an exothermal reaction. You have to temper on a constant temperature. You have to cool a little bit, and for cooling it goes a little bit up and then cooling down. So, and you cannot influence process time. This is something that is fixed, which is fixed from the kinetics of the resin. So, of the reaction kinetics. And in compare to thermoplastic, it's really slow, because the cross-linking of the polymer chains, you have to wait the reaction kinetics till its end. For thermoplastic, the process time is really short, and it's controlled by the user. So, for example, injection molding, you can directly influence with the process parameters, the injection time. You can totally influence the process temperature of the melt, but also of the mold. And of course, you are not so totally free. It depends on the dimensions of the part and what material you use. But it's sometimes you can active influence, and you first, of course, have looking on the viscosity. With the heating, the melting viscosity goes down, but not, I will show you later, not on a viscosity level like thermoset resin, it's much higher. But with the heating, melting of the viscosity, you have lowering of the viscosity. Then you have, if you have a thermoplastic prepreg, consolidation means you want to, with high pressure, get the material into the mold, or you have a thermoforming process where you have a consolidation of the thermoplastic prepreg, and then you are cooling active, and the viscosity increases because of solidification process. Okay, and you know, thermoplastic, you have no cross-linking, something you have not to wait. You can influence the plastification process directly with the temperature. You can preheat, and you can melt it once more, and you can make a solidification as you want. Okay. So thermoplastic process is summarized shorter. You can influence it direct. It's for us, for mass production, it's more interesting than thermoset resin based processes. So, well, this is an overview to the typical processes for thermoset and thermoplastic based technologies for production of fiber composites. And well, sorry, this is not interesting today. For I think for most of all of our presentations, because thermoset, of course, is necessary and is interesting, but not so much for mass production of fiber reinforced plastics for mass production for automotive applications, and especially not here for our natural-based fiber composites. So what we then still have is not so much you have to look on. This is also something good. Extrusion, of course, I think everyone knows. Compression molding, thermoforming, and winding technology. So winding today will not be so interesting, but especially these four techniques and the combinations of it. So straightforward, starting with extrusion, I think this is especially dealing with wood plastic compound, something everyone knows. And this is something also strong market here, as I know, in Thailand. So typical product or profiles, for example, some products for civil engineering, for your houses, for your floor panels, something like this. There you have your thermoplastic material, you have especially wood fibers, but also other natural fibers. Extrusion process means you have feeder where you get inside with your chopped fibers and with a polymer matrix, and you have mixing in the twin screw extruder normally, extrusion, and you get out this profile with some form mold at the end of the extruder. So this is not so new, and I will go straight forward. Now, when you go a little bit in detail of this now interesting thermoplastic technologies for us, injection molding and compression molding. So on the left side, injection molding and compression molding on the right side, you see here details what fiber typically are used, or which fibers in the geometrical form are typically used. So for both injection molding and compression molding, you can use short fiber, which is a definition. We say short fiber is something with a fiber length always looked on the part with zero below 1 millimeter. This is short fiber. Something between 1 millimeter to 10 millimeters. This is something different in the literature and also in the state of the art. This is something we call long fiber, so between 1 millimeter and 10 millimeters. And then we have something endless fiber. We call all parts with fibers where the fiber length is similar to the dimensions of the part. So if you have a typical shaped plain part, so the fibers should go from one end to the other end. Okay? So, and for injection molding technique, this is something normal. This is not so normal to use endless fibers in the injection molding process. Why and how you can use it, I will explain later. And compression molding especially is suitable for long and endless fiber based materials. So these techniques always are